chemical shift in NMR spectroscopy. It is represented by the symbol delta. Chemical shift is the position of signals and it represents the precessional frequency of the proton. As we have already discussed about the precessional frequency of the proton in basic concepts of NMR spectroscopy, right now we will consider this figure. Here, nucleus is surrounded by the electronic environment where when we apply the external magnetic field V0, the electrons here they will align themselves their movement in such a direction that it will generate the magnetic field of their own. That magnetic field generated will be called the induced magnetic moment or the induced magnetic field, which will be in the opposite direction to that of this applied magnetic field. So this induced magnetic field will try to cancel the effect of this externally applied magnetic field, and some part of the externally applied magnetic field will be cancelled by this induced magnetic field. The effective magnetic field that will experienced by this nucleus will be the deciding factor for the precessional frequency of the proton. Now if the electron density here is too high, then the induced magnetic field will be higher. So the effective magnetic field coming out of this externally applied magnetic field to the nucleus will be very less. And if the electron density here is less, then the generated magnetic field, that is induced magnetic field, will be also very less. So the effective magnetic field that is coming out of this externally applied magnetic field to the nucleus will be very, very high. To understand this, we can generalize by this formula that effective magnetic field will be equals to the difference of the externally applied magnetic field to that of the induced magnetic field. Using this concept, let us see some problems to understand the chemical shift in more detail. Here in this example we have methane molecule. Its protons will be in the 2 electrons environment. Now if we replace this one of the proton by electronegative atoms like bromine, then due to inductive effect the electron density here in these protons will be less. That means the electron density is less, we can say the protons here it is deshielded, and the protons here will bear the electron density more than that of the protons which is belonging to this molecule over here. Now for effective magnetic field, the protons here it will experience the less effective magnetic field compared to the protons here, as because the electron density surrounding this proton will be higher than that of these protons here in this case. So the effective magnetic field, if we consider of lower than that of this proton here in this case, the effective magnetic field we can represent like this for these protons, and the effective magnetic field for these protons we can represent like this. So if the effective magnetic field for these protons are less, then we have discussed in the basic concepts of NMR spectroscopy that the alpha and the beta spin states of the protons, due to less effective magnetic field, the energy gap will be very less. If energy gap will be less, then that will automatically result to the low frequency, so which will give a less frequency for these protons here. And for these protons here which is having electronegative group attached to this molecule, the electron density is less compared to the above one, so the effective magnetic field will be high, which will result that the energy between the alpha and the beta spin states will be higher than that of the above case. So if energy is high, then the frequency will be higher. For this compound, the chemical shift, that is the frequency for the protons, will be at the higher value. Another example, CH3CH2Cl. Due to presence of this chlorine as an electronegative atom, inductive effect will be there. So the protons here, that is CH2 protons, will be deshielded and the CH3 protons will be shielded ones. If the CH3 protons are shielded, then the effective magnetic field for these protons will be lower than that of this proton, that is CH2 protons. So if effective magnetic field is low for this proton, then the energy level between the alpha and the beta spin states for these protons will be less compared to that of these CH2 protons. Now, for this proton, if we consider, if energy gap is less, then the frequency will be less, since we know that energy is directly proportional to frequency. So, the representation of this molecule can be shown in NMR spectrum as like this for 100 MHz instrument, that is CH3 protons will be at the low frequency region, then that of the CH2 protons will be at the high frequency region. Now if we consider this 100 MHz instrument in more detail, then we have our 100 MHz instrument 0 ppm, 1 ppm, 2 ppm. This 1 ppm, that is 1 unit of ppm, that will be set against the reference standard. So the reference we will use is TMS. So the TMS precisional frequency for this 100 MHz instrument will be 100 MHz. For TMS proton, the precisional frequency will be 100 MHz. And if 1 ppm, if we are getting any signal, then that will be ahead of 100 Hz, more than that of 100 MHz, that is we have set 0 ppm as a fixed reference standard. So above that we are getting extra 100 Hz, so that will be considered as 1 ppm, which can be written as 1 ppm is equals to 100 extra to that of 100 MHz. Similarly 2 ppm will be 200 extra added to that of 100 MHz. So likewise the NMR scale is made. So for that, chemical shift can be calculated using this formula as delta, as a chemical shift is delta, is equals to observed shift in Hertz divided by operating frequency in megahertz. As we have discussed above, the operating frequency, that will be in megahertz. So observed shift in Hertz and the operating frequency in megahertz, we will multiply it with 10 to the power 6 to get numbers between 0 to 12. So that will be written in the form of parts per million, that is ppm. So to have a clear idea in this, let us consider this problem below. We have precisional frequency of proton is 700 Hz, greater than that of the TMS at 300 MHz instrument, where we need to calculate the precisional frequency of this proton at 500 MHz instrument. Let us see this in detail. As we have written above, that chemical shift delta is equal to observed shift in Hertz divided by the operating frequency in megahertz. We knew that the operating frequency for this instrument is 300 MHz, which is given in the question, and observed frequency is 700 Hz, which is greater than that of the TMS. So the observed shift will be 700 Hz and the operating frequency will be operating frequency will be 300 MHz, which can be written down like this. For that we have 300 MHz, so the 300 MHz can be written as 3 into 10 to the power 6 Hz. Now if we multiply it with 10 to the power 6, then we will get it as 2.3, that is 2.3 as a numerical value. Using this as it is, we will get 2.3 into 10 to the power minus 6, that is minus 6 can be called as parts per million. So we will have 2.3, that is 2.3 parts per million. So precessional frequency of proton, that is 700 MHz greater than that of TMS at 300 MHz instrument. The 700 Hz greater than TMS means 2.3 ppm for 300 MHz instrument. Now considering this, we need to calculate the precessional frequency of this proton at 500 MHz instrument. So for that, we need to find the precessional frequency. So if we consider this precessional frequency, then since this 2.3 ppm is the location of chemical shift in 300 MHz instrument, that chemical shift will be constant for every scale instrument, that is for 300 MHz instrument also and 500 MHz instrument also. This chemical shift will be fixed. So fixing this chemical shift, that is value of delta as 2.3 parts per million, then we can write for 500 MHz instrument 2.3 into 500, that is 2.3 into 500 will get parts per million, that is precessional frequency of the required proton. We will get 2.3 into 500 MHz, we will get 1165 Hz. So which can be represented as like this in 500 MHz instrument. That will be ahead of 1165 Hz frequency to that of the reference standard, so which will be 2.3 ppm. 3 ppm here for 500 MHz instrument, 2.3 ppm here for 300 MHz instrument. So the chemical shift with the unit of ppm, it is constant for 300 MHz instrument and 500 MHz instrument also. But if you see here, it is 700 Hz with the frequency as a chemical shift and 1165 Hz in 500 MHz instrument. So with the change in instrument frequency 300 to 500 MHz instrument, the frequency is also getting changed. So with that, the frequency here, it is dependent of the operating frequency. Thus, we can come to the conclusion about chemical shift that chemical shift in Hertz, it is non-standard as it is dependent of operating frequency, and ppm, it is independent of operating frequency, so ppm is standard unit. Let us proceed further with some of the important chemical shifts in proton NMR spectroscopy. This is our NMR scale, which is shown from 0 to 12 chemical shifts in ppm. Before going through this, let us have an idea about shielding, proton shielding and proton deshielding again. As we have seen above that if proton is shielded, then it will have a low frequency and it will show a low chemical shift, that is low chemical shift around this region, that is called upfield. And if the proton having deshielded, then it will show high frequency, therefore it will have a high chemical shift, that is around this region, which is also called downfield. Now, going through this NMR scale here, we have from 0, it is 0.5. So from 0.5 to 2, it is that proton which is attached to carbon, which is sp3 hybridized. Without any electronegative attachment to this carbon, this proton will show the chemical shift around 0.5 to 2. Similarly, from 2 to 2.5, it is that proton directly attached to carbon, which is neighboring to the carbonyl group over here. So due to this carbonyl group here, it will have a high electron demand to this carbon. Automatically, this proton will get deshielded more than that of this proton. So this proton will have chemical shift from 2 to 2.5. From 2.5 to 5, it is this proton which will have attachment with the carbon directly attached to the electronegative group, and this carbon is sp3 hybridized. Here this carbon is sp3 hybridized. So due to direct attachment of the electronegative group, this proton will get more and more deshielded than that of this proton. Here the carbon here, it is neighboring to that of the carbon bearing the oxygen here, that is electronegative atom, but here this carbon is directly attached to the electronegative atom, so its chemical shift will be greater than that of this proton, which ranges from 2.5 to 5. Similarly, if we see here this proton here, which is double bonded carbon, that is sp2 hybridized, which will have a chemical shift around 5 to 6.5. Now if we explain this by using the hybridization concept, then this will be seen as like that. The percentage S character for this carbon is more here, so it is near to about the nucleus. Thus this proton will get more deshielding than that of this proton here, which is attached to the sp3 hybridized. But that concept, in one way, if we see, it will not fulfill the criteria for this proton which is attached to this carbon, that is sp hybridized and triple bonded here, which ranges from 1.5 to 3. So this concept for this proton which is attached to the carbon with triple bond and sp hybridized, which ranges from 1.5 to 3, this is explained by anisotropic effect later on. Here also from 6.5 to 8.5, it is that aromatic proton. This will be also explained by anisotropic effect. Here in this case of aldehydic proton, it will be around 8.5 to 10, and in case of 10 to 12.5, it is carboxylic proton. Now we will proceed further with the concept of anisotropic effect. We will consider the benzene molecule. In case of benzene molecule, we have benzene molecule which is drawn here as like this. Benzene ring can be drawn as like this in a plane. So the electrons density in benzene ring here, they will be in this ring at a resonance. So once we apply the external magnetic field, that is B naught, the electrons here, they will align their movements in such a direction that the magnetic field will generated, that is induced magnetic field will get generated, which will be in the opposite direction to that of the applied magnetic field. So due to that induced magnetic field, the effective magnetic field around this region will be very, very low, and that will be given by effective magnetic field is equals to the difference of the externally applied magnetic field to that of the induced magnetic field, which we have discussed above. Now once we complete this circle, that is this magnetic field, When we reach here at the outer region of this benzene ring where the proton lies, the magnetic field is at the same direction to that of the externally applied magnetic field. So here the magnetic field is aligning in the direction of the applied magnetic field. So these two will get overlap to each other. The effective magnetic field to this proton here, due to overlap of this magnetic field with each other, will be high. That is, after adding these two induced magnetic field with that of the applied magnetic field will give the effective magnetic field for this proton here. So this proton will resonate at higher frequency. Hence, if this proton resonates at higher frequency, then at this region we can say it is paramagnetic, and once it completes the loop, this region is called diamagnetic. Since it is opposing, so this region is called diamagnetic region, and the region outside of the benzene ring, it is called paramagnetic region. So if it is paramagnetic region, then with change in the direction of the magnetic field, it is also changing its behavior towards the applied magnetic field. So hence this is called a anisotropic effect. So this is how we define the anisotropic effect of this benzene rings proton. That's why its chemical shift lies from the 6.5 to 8.5. Similarly, we can consider this carbon triple bonded attachment of the proton using the acetylene molecule like this. Here this carbon and this carbon, both of them are sp hybridized, and they will have a lobe which is unhybridized, and these lobes are perpendicular to each other. This unhybridized lobes, it will face them a electron cloud, and this electron cloud can be represented as like this. Now once we apply the external magnetic field B naught, this electron cloud will make a movement, and due to that it will fetch a cylindrical electron density around the acetylene molecule, and due to that cylindrical electron density environment, and this proton falls under the diamagnetic region. Due to that, this proton falls under the diamagnetic region, and the anisotropic effect of the carbon triple bond carbon over here in acetylene molecule, the chemical shift of this proton that lies in the range of between 1.5 to 3. Similarly, we can consider this proton over here, which is attached to the sp2 hybridized carbon and having a double bond in it. So this pi bond here, this is responsible for the anisotropic effect, which will give a chemical shift between 5 to 6.5. Now, if we consider the proton here, that is aldehydic proton, then this aldehydic proton can be represented as like this. Here, this is aldehydic proton, and in equivalent structure we can write it as like this here. Now the proton here, that is aldehydic proton, it lies in the paramagnetic zone of this carbonyl double bond. So due to that, it will have a high chemical shift. This is one reason. Another reason, if we see the polar structure of the carbonyl group here, the carbon is positively charged here. Due to this positively charged carbon here, it will create more dishielding to the aldehydic proton. That's why the aldehydic proton will have a high chemical shift that ranges from 8.5 to 10. With this, some important chemical shift, we can solve the unknown structure of the molecule using this chemical shift value of different protons. And if you like my videos, don't forget to share it to your friends, giving thumbs up right down below. Thank you.